Log on, tune in, find out. Another good idea from Cambridge.
Field Day. Very pleased to have Charlie Curtis here from Oregon. He'll speak to us about the refinement of the Bruhat decomposition and structural constants of Hecke algebras, Chevally groups.
Thank you. Well, I'm pleased to have an opportunity to speak here. I'll begin with some notation. So G will be a Chevally group over a finite field. Of characteristic P. And as a reference, I will give Steinberg's lectures on Chevally groups. I'm going to present an algorithm in this talk, and many of the results in those notes are presented in an algorithmic way. So B will be a Borel subgroup, and B can be written as UT, where T is a maximal torus, and U is the unipotent radical of B, or the, since we're working in a finite group here, the OP subgroup of B. Then N will denote the normalizer of T, and W the Weyl group. And as a set of distinguished generators of the Weyl group, I'll choose S1 up to Sn. And recall that W is a finite Coxeter group with these generators. And let phi be the root system of G with respect to T, and phi plus or minus the positive, respectively negative roots, and let alpha 1 up to alpha n be a set of simple roots corresponding to the generators of W. Then, by the Bruhat decomposition, the double cosets with respect to B are parameterized by the elements in W, and the double cosets with respect to U, which will be the focus of our attention towards the end, are parameterized by the elements of N. Now let W, X, Y be three arbitrary elements of the Weyl group. Then in his paper on Hecke algebras of Chevally groups, Iwahori considered the set of representatives of the left B cosets in BWB intersect YB X inverse B, and showed that a set of representatives would be UW W dot. Where W dot, X dot, Y dot are in elements of N corresponding to these elements in W, and where UW is U intersect WB minus W inverse, where this is the opposite Borel subgroup. So the, as Iwahori showed, I'll say a little more about this in a minute, the cardinality of this set is the structure constant in the Iwahori-Hecke algebra of the standard basis elements corresponding to W, X, and Y, and so it's the structure constant EW. And the main result that I'm going to describe is a decomposition of this this set in terms of the root subgroups of G by an algorithm based on a fixed reduced expression of the element W dot. And this will ultimately be used to obtain the double cosets relative to U in a form that can be applied to questions in representation theory. So let me first mention from the Steinberg notes a normalization that if we take a reduced expression of W, then we can obtain, we can choose representatives corresponding to these generators in a special way so that the representatives in N are determined independently of the reduced expression. And the way one does that is to use the fact that there is a homomorphism phi alpha I from SL to K into G, and if we let if we take phi alpha I of this element, then if we choose the generators in the form W alpha I Ti for some elements, some fixed elements in the finite field K, then these expressions Sk dot S1 dot then these representatives of W are uniquely determined independently of the choice of the reduced expression. So, as I have said, this structure constant is the cardinality of this set. And Kawanaka gave a formula for these structure constants. Where these taus are certain sub-expressions of the reduced expression for W. Which I'll call K sequences in what follows. And the decomposition of these sets that I'll describe will be in terms of pieces parameterized by these sub-expressions defined by Kawanaka, so that the result can be viewed as a geometric version of Kawanaka's formula. I should also mention that we can also consider the Chevally group over the algebraic closure of K. Then this is a connected semi-simple algebraic group, and we will obtain a description of these sets in the algebraic group as unions of subvarieties. The sets here are in the algebraic group are closed sets closed subsets defined over the finite field, and the pieces that we'll obtain will be subvarieties of these closed sets. So now let me mention what these sub-expressions are. So, of a fixed reduced expression, then this is a sequence tau k, tau 1, tau 0 with tau 0 equals 1, and tau j inverse equals either Sj or 1. For j equals 1, 2, and so on. So the terminal elements of a sub-expression are simply the elements that are less than or equal to W in the Bruhat order.
Tau j minus 1 minus inverse.
Excuse me?
Tau j times tau j inverse. Is this what you mean? I don't understand. You wrote tau j times tau j inverse.
Oh, right. Thanks. And so the terminal elements then are the set of elements that are less than or equal to W in the Bruhat order. And the sub-expression tau is a K sequence if it satisfies the following condition, that tau K x equals y is a K sequence for the triple W, X, Y, if tau K x equals Y, and so if you let J tau be the set of J's such that tau J J minus 1 inverse is equal to Sj. Then the elements of Sj are the places where the factor is not omitted, and the condition to be a K sequence is a length condition that L, SP, tau Jx is less than or equal to the length of tau Jx for each J in J tau. So if this is an element in J tau, so we have an Sj here, we work from right to left, then this length condition is satisfied for all P in the interval from J to the next element of J tau. So P in the interval from J to the next element. Or if J is the last element, then this condition is satisfied for all the generators SP after that one. And then the numbers that appear in Kawanaka's formula are given as follows, that A tau is the cardinality of J tau minus, where this is the set of elements in J tau such that the length of Sj tau J prime x is less than or equal to the length of tau j prime x, where tau j prime is the predecessor of j in the set j tau. And then b tau in Kawanaka's formula is the set of elements j different from 0, such that tau j minus 1 inverse is equal to 1. It's the number of omitted factors. Now the algorithm for UWW B intersect the algorithm for this set proceeds in two steps. For the first, we let U W X Y be the set of elements U in UW such that U WB intersect Y is not empty. Then the first step decomposes this set as a union of cells, and that UWXY is the disjoint union over the K sequences for WXY, where these are non-empty subsets, and for each one there is an explicitly given bijection in the finite case and an isomorphism of varieties in the case of the algebraic group, where where U tau is given by a product over a subset of the positive roots of positive roots depending on the K sequence tau. So this is isomorphic to the product of the additive groups of the root subgroups, or if you like, the additive group of the field. The direct product with the product of over another set of positive roots, where here we have the non-identity elements, or pieces that are isomorphic to the multiplicative group of the field, where the cardinality of phi tau is this number A tau, and the cardinality of this other set is B tau. And as you can imagine, this is a combinatorial proof. Which is based on the root structure in the group G. And the idea is this, that if we start with the reduced expression, then SKW will be a shorter reduced expression, and we use the fact that UW is U alpha K SK U SKW SK inverse with uniqueness of expression. So this is just a standard result about the root structure, and one can give the proof starting with this idea, and then using the fact that these subsets U W X Y is obtained from subsets SKW X prime Y prime, where the X prime and Y prime are given by the nature of the K sequence that we're interested in. So we always have tau a K sequence here for W X, Y. And then by a combinatorial argument, we can see how this is built up from smaller ones. Let me make a remark about this result, that the idea of obtaining these decompositions like this was first carried out, as far as I know, by Deodar, who considered what are sometimes called double Schubert cells. BWB intersect B minus XB embedded in the, or projected into the flag variety. And Deodar proved that these sets are non-empty if and only if X is less than or equal to W in the Bruhat order. And he gave a decomposition of these sets in the flag variety as unions of cells where the sigmas are sub-expressions of a reduced expression of W. And I won't go into his definition of the sub-expressions. It's based on the Bruhat order and is quite different from the K sequences. But it turns out that Deodar's results can be incorporated in the general picture that I've described. That the distinguished sub-expressions sigma of Deodar that appear in this decomposition are equal to the K sequences for, well, if you just look at this, you can see that this is BWB intersect, so this is W0B, W0X, B, where W0 is the longest element in W. And so these are the K sequences for W0X inverse W0, and one can prove that the distinguished sub-expressions as defined by Deodar coincide with these K sequences, and that the numbers attached to the K sequences in Deodar's case, that Deodar proved that these D sigmas are also products of a certain number of copies of the additive group and the multiplicative group, and that the number of factors agree with the A taus and B taus for sub-expressions here, and finally that there's an isomorphism of algebraic varieties of the U taus for sub-expressions of these elements with the cells that Deodar defined if these sub-expressions are the same. So that this was something that quite a while before I realized that one could show that this setup of Deodar's really could be incorporated in this, but so that one does have a consistent picture of the whole subject. Now, let's begin to get to the object of the talk. That the second thing we need to do is to apply these methods to the structure constants of the Hecke algebra of the Gelfand-Greve representation of a Gelfand-Greve representation of G. So let me recall what that is. It's we take a linear character on U in general position. Then the Gelfand-Greve character gamma is the induced character, and it is known that if it is if the linear character is in general position, then the Gelfand-Greve character is multiplicity free, and the decomposition was obtained, for example, in terms of the RT thetas by Deline and Lustig in case the center of the group is connected. And we are interested in the Hecke algebra, or the endomorphism algebra of this induced character. So we let E be the linear character, the idempotent corresponding to the linear character C in the group algebra. And the Hecke algebra is E, CGE, and a basis then will consist of, well, it's clear because this is a character in the group algebra, an idempotent in the group algebra of U, that if we take the representatives of the UU double cosets, which are the elements of N, then a basis will consist of the elements E, N, E, different from 0, where N is in the normalizer of the torus. And we can obtain what are called standard basis elements by multiplying by a factor, so that the structure constants are actually algebraic integers. And a formula for the structure constants is given as follows. So let L, M, N belong to N, then the structure constant is so the multiplication then is given like this. And this formula for the structure constant is that this is equal to the order of U times that one analyzes the convolution product of these elements and obtains this formula. And here, just as in the case considered earlier, UN is U intersect N UM. N B minus N inverse, and ALY is U inverse times CU1 inverse C U2 inverse if y is U1L U2 with L and N, these elements in U, and and is equal to 0 if y is not in this double coset. So now we see from this formula that in order to obtain the structure constants of the Gelfand-Greve representation, we have to determine these intersections. And so we have to go from the previous discussion, which dealt with the double cosets relative to B, to the double cosets relative to U. And the algorithm that we had earlier is sufficiently powerful to give this information. So, and it goes like this. So, let L, M, N in N correspond to W, X, Y in W as before. Then write L equals so we take these fixed representatives of W, X, Y that have been used earlier, and these elements in N then are obtained by multiplying them by elements of the torus, which are determined by the multiplication in the group as obtained in the Steinberg notes. So this would be X, TX, and so on. Then UL, LB. Intersect N, U, N inverse, M inverse is just T prime Y. So it's obtained from the piece that we already know. UWWB intersect YU X inverse. Yes. And the triples U1 V in U W U U M inverse are known by the algorithm. So I should, in a little more detail, UW W dot B intersect U intersect Y U X inverse can be identified with the triples U B V with satisfying U W dot B is Y dot V X dot inverse with U in UW and B and so on. And the point is, and B and V are uniquely determined by U. Then if we let the theorem is that that U W B intersects Y U X inverse identified with this set of triples is a union over K sequences of U W WB intersect Y U X inverse tau, where this set is simply this set of triples U V V with U in U tau and B in B and V. So this set then is the disjoint union over the K sequences for W, X, and Y of these subsets, and these subsets in turn are given by the algorithm starting from the elements in those cells, the U taus. So it is possible then to obtain the structure constants for the Hecke algebra in this way. Now here's the motivation for all this, that H, the Hecke algebra of the Gelfand-Greve representation is a commutative algebra. And we know the structure constants now, CL, CM, Cn. So from 19th century mathematics, we know that the representations of H are given by the eigenvalues of the matrices CL, CM, Cn, giving the regular representation on the commutative algebra. Now the representations of H are known to be determined by the geometric conjugacy classes in the group. If we identify the Chevally group now with the finite reductive group, and so for each geometric conjugacy class T theta, there corresponds a representation of H, or a spherical function, or a twisted spherical function in the terminology of McDonald's book. And this in turn corresponds, by the theory of Hecke algebras, to an irreducible character of G, which is characterized, chi t theta, characterized as the unique irreducible character of G, such that chi t theta appears with non-zero multiplicity in gamma and with non-zero multiplicity in the Deligne-Lustig virtual character RT theta. So we now know that the values of the representations ft theta at the standard basis elements are given by the eigenvalues of the these matrices. And so the problem now is to investigate these eigenvalues and find their connection with the Deligne-Lustig characters. Thank you.
How did Kawanaka prove his result if he did not?
Excuse
How
me?
did Kawanaka prove his result if he did not kind of obtain the decomposition into pieces?
By computations in the Iwahori-Hecke algebra. You see, using the generators and relations in the Iwahori-Hecke algebra, he was able to it's done by induction, and using the using the and the whole,
You don't need the cell decomposition.
what's that?
You don't need a cell decomposition in order
No,
to calculate the
no,
structure.
that you can simply
This is
use
combinatorics.
the defining relations in the Hecke algebra to calculate the structure constants in that case.
Did he estimate these numbers A tau and B tau, or just he said that they exist? Did he estimate these two numbers A tau and B tau? See, in the formula there was summation of the tau of Q
Yes,
to the A
yes,
tau.
and the A tau and the B tau are given in terms of the sequences explicitly.
Yeah,
Yeah.
Did he do it, or you?
You know, he did it.
I did.
He obtained the formulas for the A tau and B tau, but the connection with the geometry
No, I understand.
is what I managed to figure out.
There is a version for twisted Chevally groups, I guess. Or
Yes, and also I have begun to investigate this decomposition for p-adic groups. One can start with the Iwahori Matsumoto paper, and it may be possible to carry out a similar analysis there.